So in today's video, we're going to look at chapter 8.4, which is called Applications of the Normal Distribution. This chapter is actually very, very similar to 8.3, and it actually leads on from it. So in 8.3, we looked at the standard normal distribution. So the standard normal distribution is where you have this normal distribution, so your data follows that curve, but you have a mean of 0 and a standard deviation of 1. So in the standard normal distribution that we saw last time, when you drew that curve of your data, so it is the curve of the histogram, so you would obviously have bars underneath for the frequency of each one of these, but it follows that curve. Your mean is right down the middle, and in standard normal, you have a mean of 0 and a standard deviation of 1. So 68% of your data, roughly, lies between the actual values of -1 and 1. And it just so happens that 1 is your standard deviation in this case. Then you would have roughly 95% of your data lies between -2 and 2, and roughly 99.7% of your data lies between -3 and 3. Okay? With any other normal distribution, which is what we're going to look at today, it's not necessarily the standard normal distribution, you may come across a situation where, again, you've got this normal distribution curve, but your data may be centered at any random value. Okay, your mean is no longer 0. Your mean is any value, okay, not necessarily 0. And your standard deviation may not be 1, okay? So you're going to have each of these values is just now the mean plus 1 standard deviation, the mean plus 2 standard deviation, and the mean plus 3 standard deviations, and you're going to subtract multiples of the standard deviation away on this side. Okay, so this time your mean is not necessarily 0, and your standard deviation may not necessarily be 1. Okay, they are going to be some other values. The question is, when we did this in 8.3, okay, we were looking at, okay, what is the probability of landing between two values? So we looked at, let's take a z value of, let's say, 1.27. What's the probability that you have an outcome that is greater than 1.27? Okay, well, in that case, we looked at where 1.27 was on our standard normal distribution graph, and then we found the area under the curve. If we were looking greater than 1.27, we look at the area under the curve to the right of that value. We could use our calculators of using when we did the normal CDF function on our calculators, 1.27 would be our lower bound and 10 would be our upper bound, and then we would have a mean of 0 and a standard deviation of 1. But how do we do those calculations when we don't have a mean of 0 and a standard deviation of 1? Can we still use normal CDF to find those probabilities, to find those areas? And can we still use inverse norm in order to find our values? Well, the answer is yes, but the main issue that you come across is actually looking at an example like I just said, okay? I said to you something along the lines of, what is the probability of getting an outcome that is greater than 1.27? Okay, so if we're in standard normal, okay, we know that we're going to put in normal CDF with a lower bound of 1.27, an upper bound of 10, a mean of 0 and a standard deviation of 1. Let's say we were doing that same type of problem, but this time just in a normal distribution sense. And I said, what is the probability of getting an outcome greater than some certain value? Okay, so let's say we're going for a value that may be, I don't know, around here somewhere. What's the probability of getting greater than that particular value? An outcome that's greater than that value? Well, again, we would use normal CDF. The value would be your lower bound, But now your issue is, what is your upper bound? Okay, 10 is no longer 10 standard deviations above the mean. Okay, 10 is now just some random value on this graph. You may not even see it anywhere on this graph. If your mean is, let's say, 10,000 and your standard deviation is 1,000, okay, 10 would be all the way down here, okay? That would make no sense if we're looking at the probability that we're between this value and above, okay? Using a value of 10 would make no sense in a situation where you've got a very large mean and a very large standard deviation. 10 means nothing to us. So the problem we now have is, what is our upper bound? In the same way, if we were dealing with a problem where we were looking at what's the probability of having an outcome that's less than a certain value, what do you use as your lower bound? We can no longer use negative 10, because negative 10, it may not even be lower than the mean, okay? It may be like way too large, okay? Or it may be way too small compared to what we're actually dealing with, okay? So this is the type of problem that we run into, trying to find a lower and upper bound when we are not dealing with the standard normal distribution, okay? Because we can no longer use 10 and negative 10 as being 10 standard deviations away from the mean. So what values do we use? Well, this is where I talked about in 8.3, something called a Z transformation. And that is why the standard normal distribution is also called a Z distribution, because we use that actual letter Z to denote our value. So I would have said in this particular problem, what is the probability of getting an outcome greater than Z is equal to 1.27? All of my values here in my standard normal distribution, my values are always denoted as Z. If I don't have a mean of 0 and a standard deviation of 1, so I'm no longer in standard normal, but I am just in a random normal distribution with a random mean and random standard deviation, my values are called X, okay? I use X as my variable. So if you ever see Z, you know you're dealing with standard normal. If you see X, you know you're just dealing with a normal distribution that doesn't have a mean of 0 and standard deviation of 1. So, as I said, this means that this standard normal distribution is also called the Z distribution, because we can actually do something called a Z transformation. What is a Z transformation? Well, a Z transformation will turn data that has a normal distribution into a standard normal distribution. Okay, so what a Z transformation does is it takes a set of data and it takes one of these graphs that just has normal distribution. So it's got some random mean and a random standard deviation. And it turns it into data that has a standard normal distribution. So it brings the mean back to 0 and it brings the standard deviation back to 1. Once you have done that to your data, what you can then do is run all of your calculations like we did in 8.3, using those same calculations that we did in the standard normal distribution, where we can use an upper bound of 10 and we can use a lower bound of negative 10. We can use a mean of 0, we can use a standard deviation of 1. So you can take any normal distribution that has any mean and any standard deviation that may be really difficult to deal with and kind of difficult to visualize, and it pulls it back to a standard normal distribution where you've got a mean of 0 and a standard deviation of 1, and it is way easier to do calculations. Question is, what is the Z transformation? Well, there is a formula for it, and it's actually not too difficult to remember and understand once you see what is going on here. What a Z transformation does is it takes each of the data points X in your normal distribution. So remember, X is in the normal distribution where you have these data points that have a normal distribution with a random mean of mu and a standard deviation of sigma. So x is each one of your data points. And what it does to each of those data points is it subtracts the mean from it. So you are taking all of your data points and you are subtracting the mean. What does that do? Well, let's go ahead and look at a diagram. I'm going to draw this out. So let's say that this is the graph of your normal distribution. So this is a normal distribution with a mean, we'll call it mu, and a standard deviation, we'll call it sigma. Okay, so your mean mu is right down the middle, and each one of these, I'm going to plot out my standard deviations either side. So this is what our diagram will look like for our normal distribution. Okay, so I've subtracted up to a multiple of 3 standard deviations and added a multiple up to 3 standard deviations. So I've got this diagram with my mean right down the middle. On my top line, what I am doing to this data is subtracting the mean from it first. So I'm taking all of my data points on this curve and I'm subtracting the mean from them. Well, if I'm subtracting the mean, I'm going to be shifting my graph to the left by that value of the mean. So I'm subtracting the mean off of each of my data points. So what does that do to it? Okay, let's plot this out again. If I'm subtracting the mean, let's look at the data point that is right here at the mean. Where does that point move to? Well, it's originally at the mean mu. We're subtracting the mean from it. So if we subtract the mean from each one of these, it's easiest to see with these data points, they're actually plotted out. I'm subtracting the mean from each of those. I'm actually doing it to every single data point, but we'll look at these major data points, okay? If I subtract the mean from the data point that is at the mean, I'm going to get 0. So that's going to shift that data point back to 0. If I subtract the mean from this data point, I'm going to end up at sigma. If I subtract the mean from this data point, I'm going to end up at 2 sigma. And you're going to do that for every single one of your data points. And what you see is it actually just shifts that graph back by however many units mu is. Okay, so let's say your mean was 3. Okay, it's going to shift all of your data points back by 3. Okay, that leaves you with this graph. Okay, so now your graph is now centered on 0. 0 is now your mean. Okay, which is great. The problem is I've still got some random standard deviation going on, okay, whatever sigma is, okay. Let's say you had a standard deviation of 2, okay, then I would have 2, 4, 6, etc. Okay, so whatever your standard deviation is, it's not necessarily 1 at the moment, okay. So we have some random data points happening here. What we would really like is a standard deviation of 1. So what can I do? Go back to our formula here, okay? I've subtracted the mean from each of my data points, which shifts my whole graph back by mu units. What I'm then doing is I'm then dividing by sigma. What does that do? Well, when you divide each of your data points by a certain value, it's actually either going to squish or enlarge your graph. So either it's going to like squish it inwards like that, or it's going to flatten it outwards by moving it out, and it's going to flatten that curve, okay? So when you divide by sigma, okay, it's actually going to change what this curve will look like slightly. But look at what it does to each of my data points, okay? For that data point that is right here at sigma, okay, what's it going to do to that? Well, I'm going to take sigma and divide it by sigma, okay? Because all I'm doing to each of my data points now is dividing by sigma. So this data point here is going to go to 1 because I'm dividing it by sigma. This data point here that's at 2 sigma, I'm dividing it by sigma. That's going to go to 2. This data point here at 3 sigma, I'm dividing it by sigma. That's going to go to 3. So you can see what is happening here, okay? The one that's at 0, I divide 0 by anything, I'm still going to get 0. So my mean still remains at 0. but each of my other data points gets divided by sigma, and it's either going to squish this graph together and actually make the curve steeper, or it's going to enlarge the graph and stretch it out and flatten that curve, okay, when you divide by a value. But what it does to each of my data points and what it actually does to my standard deviation is move it back to 1. So your final graph, when you draw this out, whether it be squished together and actually get taller and steeper, or whether it actually flattens that curve and stretches it out, you end up back with a mean at 0 and a standard deviation of 1. Okay, so what that Z transformation does is it took your original data set and your original normal distribution curve with a random mean and random standard deviation. It shifts the graph along the x-axis to give you a mean of 0, and then it will either flatten the curve or steepen the curve to give you a standard deviation of 1. Okay, so that's what that Z transformation actually does. This is a very important formula. Make sure you remember it, okay? Because it takes each of your x values in your normal distribution and transforms it to a Z value, so then you can go ahead and use a mean of 0 and a standard deviation of 1, okay? That's why we like it. So let's go ahead and do some examples of this, okay? Some of these you can either use a Z transformation, or in some cases you can actually just go ahead and plug some stuff into your calculator. It depends on the type of problem, and I will show you that as we go through. Okay, so the first example that I'm going to do is to find the probability that a normal random variable, so we're not in standard normal anymore, I know it's just a normal random variable, we're going to have a different mean and a different standard deviation. Okay, we're going to have a mean of 10 and standard deviation of 20 will lie between 10 and 40, okay? So I want the probability of finding an outcome, of finding a normal random variable with a mean of 10 and a standard deviation of 20, of landing, of finding an outcome between 10 and 40. Whenever you get one of these, and I always encourage people to do this with anything to do with normal probability, please draw it out before you do anything else, okay? Before you even touch your calculator, make sure you draw it out so you can actually visualize what you're calculating, and it makes it so much easier to see what you're doing, okay? So let's go ahead and sketch out a curve quickly so we can see what's actually happening. Okay, so I know that I've got a mean of 10, so 10 is right down the middle, and I've got a standard deviation of 20. So if I start adding multiples and subtracting multiples of the standard deviation, just so I can see roughly where my data lies. Remember, I'm going to have roughly 68% of my data within one standard deviation of the mean. So between -10 and 30, okay, so I've subtracted one standard deviation from the mean and added one standard deviation to the mean. Okay, between -10 and 30, I should have roughly 68% of my data between those two values. Okay, let's add and subtract another multiple of the standard deviation. So between 50 and -30, I should have roughly 95% of my data. And one more. Between -50 and 70, I should have 99.7% of my data. So almost all of my data lies between those two values. Okay, let me get rid of those lines for a second. Okay. My problem is I want to look between 10 and 40. So between the mean, which is 10, and between 40, which is right here, I want to know the area under the curve between those 2 points. I want the probability of landing between those 2 points. Okay? Whenever you are looking for an area or probability, okay, because it's the same thing, the probability is the area under the curve between those 2 points, you use normal CDF. Okay, it's exactly the same as last time. We're going to use normal CDF. If you're looking for values, you use inverse norm. But for area or probability, you use normal CDF on the calculator. Now, same deal as before. Okay, this one is slightly easier, but I'm going to do this 2 ways to prove a point. Okay, some of these, there's only one way of doing it. And some of these, there's actually 2 different ways depending. One's actually easier than the other, but I want to do it both ways to show you that it does work. Okay. So I'm going to use normal CDF because I'm looking for an area or a probability. Okay. Now, when you use normal CDF, it asks you for a lower bound, an upper bound, a mean, and a standard deviation. Okay. In this case, you have both a lower and an upper bound. They are strict lower and upper bounds. It's not a problem where it says to you, what's the probability of being greater than a certain value? Or what's the probability of being less than a certain value? Okay. You have a strict upper and lower bound. In those cases, you can just go ahead and plug it into your calculator. You do not need to do a Z transformation. I'm going to do it using a Z transformation to prove that you get the same answer, but you do not need to do that, okay? In this particular case, because you know you've got a lower bound of 10, that's the lowest value that we want to look at, and an upper bound of 40, then you've got a mean of 10, and you've got a standard deviation of 20, okay? You have a strict lower and upper bound. It's not like an open-ended greater than a certain value or less than a certain value, where before we would have plugged in 10 or negative 10 for our lower or upper bounds. You don't have to deal with that in this situation. And this is a good example of where you couldn't just use 10 or negative 10 as your lower and upper bounds, okay? In this particular problem, okay, that wouldn't have been good enough. 10 is not far enough away. 10 is actually your mean, okay? So 10 wouldn't have been so far away from your mean that we could then use that as an upper bound. And negative 10 isn't so far away from the mean that we could use it as a far off lower bound, okay? So this is a good example of that. But in this case, because they have given you a strict lower and upper bound, they've given you the mean and they've given you the standard deviation, we can just plug that into our calculators and it should come out to 0.4332 if you try it on your calculator, and I highly encourage you to do so. Okay, so in the case where you have a strict upper and lower bound, so it's not an open-ended greater than or less than a certain value. You can use normal CDF right away. Okay. Your problem comes where you do have one of these open-ended questions where it says, what's the probability that you're greater than? In this case, if it said, what's the probability that your normal random variable is greater than 10 or greater than 50 or something like that. You don't know what you can use as your upper bound. You could type in an incredibly large positive number and it would probably work, but sometimes your calculator actually doesn't like that. I know sometimes mine goes weird on me if I try to do that in a particular situation like this. So in those type of problems, you will need to do a Z transformation. So I'm going to do a Z transformation for this just to show you. Okay, so just to show you that a Z transformation works, I'm going to do that here in this particular problem. So what I'm going to do is I take each of my data points and I would have subtracted the mean and divided by the standard deviation. Okay, that will bring this back to 0. So 10 is going to be brought back to 0, and each of these data points and each of my multiples of the standard deviation above and below the mean are going to be pulled back by the mean. So each one of these, like your data points, would now be -40, oh, actually, sorry, negative 60, negative 40, negative 20, 0, 20, 40, and 60. So each one of your data points is going to be brought back, okay? Then you would divide by the standard deviation, and that would squish or expand that curve so that your standard deviation was 1. But what you will do is you will do that to each of your bounds. Okay, so what you are looking at to start with is the probability that your random variable x falls between 10 and 40. Okay, if you think about when you do a z transformation, what you are doing to each of your data points, you're subtracting the mean and dividing by the standard deviation. So I'm going to subtract the mean and divide by the standard deviation for each of my data points. So I'm going to do that to my endpoints and for my random variable x, which is any value between 10 and 40. So I'm subtracting the mean divided by the standard deviation. Okay, my mean was 10, my standard deviation was 20. So I'm going to do 10 minus 10 divided by 20. Then x minus the mean divided by the standard deviation. Well, that is just our formula for z. Okay, x minus the mean divided by the standard deviation is just z. Okay, so we know that we're back in our standard normal distribution. We know that we've got a mean of 0 and a standard deviation of 1 now. Then 40 minus my mean of 10 divided by the standard deviation of 20 is going to be 40 minus 10 divided by 20. So this simplifies to the probability that z is between 0 and 40 minus 10 is 30 divided by 20. That simplifies to 3 over 2, which is 1.5. So now we are looking at, we've transformed our normal distribution into a standard normal distribution. So instead of using x, where we've got this normal distribution, it had a mean of 10, standard deviation of 20. We are now in standard normal distribution. We have a mean of 0 and a standard deviation of 1. Our lower bound, because we have shifted those points and we have changed the shape of that curve, remember it's still a normal distribution. We still have that area of 1 underneath it, because if we expanded that curve, it would flatten it. And if we actually squish that curve together, then it would make it taller to account for that. So we've still got an area of 1 underneath our curve, but all we've done is basically shifted it around. So the areas would be the same under the curve. It's just that we are now looking between two different values because we have changed it slightly. We now have a mean of 0, standard deviation of 1, but now my lower bound is 0 and my upper bound is 1.5. So what I could have also done is done the normal CDF with a lower bound of 0, an upper bound of 1.5, then a mean of 0 and a standard deviation of 1. And that will come out to that exact same value that we had before, okay? So, as I said, when you have this strict upper and lower bound, like we have here, we had a strict upper and lower bound of 10 and 40. We didn't have to worry about dealing with an open-ended greater than or less than. When you have a strict upper and lower bound, it's easy. We can just go ahead and plug that stuff into normal CDF into our calculator with whatever mean it gives us and whatever standard deviation it gives us. Or if you want to stay consistent with the rest of the problems and just always do a Z transformation just to be safe, you could go ahead and do that, and then your lower bound would be 0, your upper bound would be 1.5, and then your mean would be 0 and your standard deviation would be 1. If you look at this, you know it's the same, like you're doing the same thing, okay? Remember, when we were dealing with this problem in our normal distribution with a mean of 10 and a standard deviation of 20, okay? Let's look at what I actually have. My mean was 10, so I was looking at the probability of being between the mean and 1.5 standard deviations above the mean, okay? 20 times 1.5 is 30. I've added 30 to 10 to give me 40, okay? So 10 was my mean and 40 was 1.5 standard deviations above my mean. That was in that normal distribution. Now I've pulled it back to standard normal distribution with a mean of 0 and standard deviation of 1. I am still looking at the probability of being between my mean and 1.5 standard deviations above the mean. So it is still the exact same problem. So don't worry, like, it's always a good check to actually do that. But don't worry about, like, how does this work? Like, we've changed the problem. You haven't. You've kept the calculation actually the same. Okay, you are still looking at, in this case, between the mean and 1.5 standard deviations above the mean. It will not change the answer. You haven't changed the problem. Okay, but as I said, with the strict upper and lower bound, it's totally up to you whether you want to do that Z transformation or not. I'm going to stick with the same mean and standard deviation. So again, we're still going to be dealing with a normal random variable. With a mean of 10 and standard deviation of 20. So I'm sticking with that same normal random variable. But now I want to find the probability of being greater than 30. Okay? So again, I would draw it out. Okay? We know, again, we've got a mean of 10 and a standard deviation of 20. So if we plot out our standard deviations above and below the mean, okay, we get that. So we want the probability of being greater than 30, which is the area under the curve to the right of 30. Okay? Now, in this case, we know that when we're looking for an area or probability, we use normal CDF. But when we do that, the issue is that we don't know what our upper bound is, okay? Before, in this situation, when we dealt with standard normal distribution with that mean of 0 and standard deviation of 1, we just used 10 as an upper bound when we needed a very large upper bound. We can't use 10 in this case, okay? 10 is actually in the other direction. So we don't have an upper bound to use. And as I said, calculators don't tend to like it if you just plug in some random massive number. Sometimes it will just go weird on you and just error out, okay? So we need a way of doing this. That's where a Z transformation comes in. So before we go ahead and use normal CDF, we need to know what upper bound to plug in. So I'm instead going to do a Z transformation. So at the moment, I am in normal distribution with a mean of 10, standard deviation of 20. Because I'm just in some random normal distribution, I'm going to use X as my variable. Okay, Z is used for standard normal, X is used for normal. So what I'm now going to do is do a Z transformation. So this is going to be the probability of X minus the mean divided by the standard deviation. And then I'm going to do 30 minus the mean divided by the standard deviation. So I've just subtracted the mean divided by the standard deviation. This thing here is our formula for Z. So we're looking at the probability that Z, now my mean is 10, my standard deviation is 20. So I'm doing 30 minus 10 divided by 20. What is that? Well, 30 minus 10 is 20, divided by 20 is just 1. So I'm looking at the probability that Z is greater than 1. I am now in standard normal. So I now know that I've got a mean of 0 and a standard deviation of 1. I have pulled the whole graph back to a mean of 0, and I have either stretched or squished the curve, so now I have a standard deviation of 1. Okay? Now, because I am in standard normal, okay, with a mean of 0 and standard deviation of 1, I now have, if I drew this out again, okay, for a standard normal curve with a mean of 0 and standard deviation of 1, Okay, I'm looking at the probability that z is greater than 1. I am looking at the area under the curve to the right of 1. Okay, because I'm in standard normal, what can I use as an upper bound when I need one? I can use 10. So now when we do normal CDF, we're going to have a lower bound of 1, an upper bound of 10, which we can now use because we are in standard normal, with a mean of 0 and a standard deviation of 1. Okay, so we now can use 10 as that upper bound. We know what we can use as an upper bound. And again, when you do that, your answer should come out to 0.1587. Okay. Now, another way that you could have done this, okay, this is just a side note again. Remember, the area under the curve is 1. So what I could have done, and I wouldn't really recommend it because it's an extra step that you don't need, but what I could have done is instead found the area under this part of the curve here. So I could have used -10 as a lower bound and 1 as an upper bound, found that yellow area, and then done 1 minus that area to find the blue area that I wanted. So again, it's like an extra step, but just to kind of combine everything together to make sure we know how this all works. What you could have done is 1 minus the value that you get if I would have used -10 as my lower bound and 1 as my upper bound, and then done 1 minus that. So that also comes out to the same answer. It's totally up to you which way you want to do it, which way makes most sense to you. But to me, what I would have done here is exactly what I did at the start. I've taken my data that was in normal distribution. I have converted it to standard normal distribution. Once I'm in standard normal distribution, I know I've got a mean of 0 and a standard deviation of 1. I've got my lower bound of 1, and I now know I can use my upper bound of 10. So the next example that I'm going to do is going to be one where I'm trying to find a value. So I'm going to use inverse norm. So I'm now going to have a mean of 28 and standard deviation of 2.5. And I want to know what is the value of the normal random variable. Okay, and remember, now that we're just in normal distribution, it's not standard normal, my variable is denoted x, that has an area to the right equal to 0.67. Okay. I would always draw this out, okay? As always, I would draw it out. So this is my normal distribution curve. My mean down the middle is 28. My standard deviation is 2.5. So I'm going to have 30.5, then I'm going to have 33, and then I'm going to have 35.5, and then subtracting 2.5, I'm going to have 25.5. Then I'm going to have 23, and then I'm going to have 20.5. Okay. Now, I want to know what is the value of the variable x such that the area to the right is equal to 0.67. Okay. Now, I know that either side of my mean, so either side of 28, I've got 50% of my data. So my area to the left of 28 is 0.5 under the curve, and my area to the right under the curve is, to the right of 28 under that curve is 0.5 as well. So I know that if the area to the right of this particular variable is equal to 0.67, I'm probably going to be somewhere to the left of the mean, because the area to the right of the variable is 0.67, and I know to the right of 28 to the right of my mean, I've got 0.5. So I need a bit more than that. I need a bit more than 0.5 to get me to 0.67. So I'm probably somewhere around where that blue dotted line is. That's roughly where my variable x is going to lie. I'm somewhere in there. I need to find that variable x. Now remember, if you're trying to find a value, when you're finding a value, you use inverse norm. Okay, so I know I've got to use the inverse norm function. But remember, when you use that inverse norm function in your calculator, you always have to plug in the area to the left of the value that you are trying to find. At the moment, I only have the area to the right, which is 0.67. I need this area to the left of it, that red area. That is what I plug in to inverse norm. It always has to be the area to the left, so don't get caught out by that. It has to be the full area to the left of the value that you are trying to find. Area under the whole curve is 1. I know I've got 0.67 to the right of the value, which leaves me with 0.33 to the left. So now I know that when I use inverse norm, okay, I need the area, the mean, and the standard deviation. I don't need to do a z transformation in this case because I can just plug in my mean of 28 and my standard deviation of 2.5, okay? I don't do a z transformation on an area. You only do z transformations on values, okay? So what this is going to give me when I plug in my area of 0.33, the area to the left of the value, then my mean of 28 and my standard deviation of 2.5, I get my x value, which is 26.9. So x, my random variable, is roughly 26.9. Okay, that makes sense with this problem, with what we have here. Okay, I knew it had to be to the left of my mean of 28, and it looks roughly right from my diagram. Okay, 26.9 seems about right. Okay, so I would always draw this out just so you can kind of double check your answer. But whenever you're dealing with inverse norm, okay, you can just plug in the mean and the standard deviation of whatever you have, because the inverse norm deals with areas to give you that value. The value that you get back will be in the normal distribution that has the mean and standard deviation that you plugged in. Okay, so we know that this is going to be a variable x. It's in a normal distribution with a mean of 28 and a standard deviation of 2.5. So now moving on to problem 4. Again, I'm going to stick with a mean of 28 and standard deviation of 2.5. So I'm going to stick with that normal random variable, that normal distribution where we've got a mean of 28 and a standard deviation of 2.5. And now I want to find a probability that the normal random variable will be between 25 and 30. Okay. This one is the same as the first one that we did. It's kind of a recap of the first one. We're just using different numbers this time, so just kind of hammering home the point. So again, let's come back to here. We are using this same curve, okay? It's the same distribution. But this time we want the probability, I'm going to do this in, I think, green. I want the probability that we are between 25, which is here, and 30, which would be roughly here. So I want the probability that I land in this section here. So between 25 and 30. Okay. It's a probability, means I'm looking at the area under the curve between those 2 points. So what do I use? I use normal CDF. So in this case, I have been given a strict upper and lower bound. I know my lower bound is 25 and my upper bound is 30. I'm not looking at a greater than or a less than, okay? I know what my bounds are. So I can just go ahead and go to normal CDF, and I can plug in my lower bound my upper bound, my mean, and my standard deviation. I do not have to do that z transformation to give me a mean of 0 and standard deviation of 1 because I have that strict upper and lower bound. Okay, so we can stick to just normal distribution. It doesn't have to be standard normal. And that should come out to 0.6731, which if we come back to our diagram, that makes sense with what we have and what our values are. And when we look at the shape of that curve, that does make sense. Okay, so bear in mind, when you are looking for an area, when you are looking for a probability, we are using normal CDF. If you have a strict upper and lower bound, you can just stick to that normal distribution with the mean and standard deviation that you are given. The problem comes when you are dealing with something where we don't have an upper bound or we don't have a lower bound. You will have to do that z transformation to get yourself into standard normal with a mean of 0 and standard deviation of 1, because then we know we can use 10 for our upper bound or negative 10 for our lower bound. Okay. That's everything for this video. Try out the homeworks. There's plenty of problems there for you to try this stuff out. If you run into any issues, let me know, and I will see you in the next video.